All right, welcome back to our series on designing a computer from scratch. This video will actually have a demo of the card running, and quite a few features are going to be added that make it pretty much a decent little computer. In the last video we hooked up the 7-segment display, and we did a pretty big refactoring of the CPU VHDL code into separate CPU and CPU top entities, files. And the CPU is just the CPU. It doesn't have any of the peripheral stuff. It does include the bus out to the peripheral, but that was a nice big step that made it a lot easier to play with the files, because each of those files is now about half the size of what the original file. We also made a new peripheral memory map for the I/O space, and we connected the UART pins up, but we didn't do anything with it. In this video we'll add a whole bunch of peripherals to the CPU. Let's dig in and see what we can do. I'd like to make use of the USB port. We have it wired, but all we did was a loopback before, and it'd be nice to put an actual UART in there for that USB to serial port. I'd like to drive something out on the VGA. That'd be kind of fun. And then do things to play with that large I/O header. I'm not going to mess with the PMOD connectors, but the I/O connectors are that big I/O connector is essentially the same thing. As usual, to find the pin numbers for the UART, we already found those, but the VGA, go to the QMTECH documentation, look up that VGA project 8_VGA, and that'll have the QSF file in there. And if you look at that QSF file, it'll have those pin numbers that you need. It's a lot easier than digging them off the schematic. Okay, let's add those two peripherals, the UART and the VGA. And first thing we want to do is find the spot in the UART or in the memory map to put them. The UART is going to be at locations 4 and 5. One of these is a control and status. If you write to it, it's a control. If you read it, it's a status. The other port will be a data port, where you write and read the data that you want to write to the device, but that'll be at 4.5 for the UART and 6.7 addresses for the VGA. Still a lot of space left in our 256 I/O space. These devices aren't, you don't write directly to the large RAM for the screen. The VGA and UART both have a legacy style 6850 interface to them, albeit in a form that's more adapted to FPGA with separate read and write strobes. The 6850 would have had a single read-write line, and then you generated data strobe, and you gate that with the read-write line. But most of these modern FPGA computers have a separate read and write strobe, and that's how these peripheral devices are all set up. But that's very easy to accommodate. So what did I do? I added them from Grant Cyril's multicomp, the UART, buffered UART, and the VGA. I did switch that out to the NC display VGA. I've got them both inside of the GitHub, so you can use whichever one you want. The NC display has quite a bit nicer fonts, and it's more configurable. The card has 565 RGB mapping for the bits, which is 5 bits of red, 6 bits of green, 5 bits of blue. That's pretty typical for these FPGA cards that have a VGA connector. They will hook up an extra bit on the green, because that's, I think the eye is less sensitive to that, or more sensitive, I forget which. But basically I just mapped that to the 222 bits from Grant's VGA, so that those 5 bits could be driven from the 2 bits that come out. That gives you a total of 2 to the 6, or 64 colors, or brightness on any colors as well. So it's a nice little way to go. The ANSI display VGA VHD file implements a complete, well, fairly complete ANSI terminal, takes the normal escape sequences and interprets those into things like screen clear, set color, set bright, set background and foreground colors, set other sorts of things that you would want to set for a display. And again, both of these have a 6850 style interface, if you're familiar with the ACIA chip from back in the 70s. The VGA test code is not very complicated. It's loaded up into the GitHub as part B3, test 1. And here's the listing file for it. First line of code reads the UART status register, which is at location 4. And then it tests the least significant bit. If that bit is 0, then it'll sit and then run until data comes in from the UART. Once it receives data, it will then read it in the register 1, and it'll echo it out both to the UART and to the video display unit, the VGA itself. So pretty tight little code here, and then I think I clipped off the jump back to 0. There'll be a return back to 0 that keeps it running forever. So I ran it and it does work. When you type in, and I've captured the PuTTY here, I didn't capture the VGA. It's a little tough to capture, but it did work. It put it up on both the VGA screen and the other, and I did a few typos, and then, hey, tested, this works, yay, party on. So good news, the VGA does work. Again, this video series is not going to be on designing peripherals that I can just find out there. There's plenty of nice peripherals out there, and we'll just use those exactly as they are. This is more on the CPU design side. We'll design a few peripherals along the way that really have to for this card, but we'll try to stick to the processor changes. But very nice at this point. You've got a UART, you got a VGA, you can do some pretty cool stuff. If the card had a PS2 connector, we could do even more. Next thing I decided to add was a timer unit, and I developed this previously, but the timer unit has 3 locations you write to. If you want to count for a 0 to 255 microseconds, you write to location 8. If you want to count for 0 to 255 milliseconds, you write to location 9. If you want to count for 0 to 255 seconds, you write to the count. Well, you might ask, what if you want to count between 256 and 1 microseconds and 1 millisecond? Well, you can just call it a couple of times. These are reasonable numbers for most of the kind of things you'd want to do. Usually you're in the orders of microseconds, milliseconds, seconds. 255 seconds, that would just get to be a lot, but more perfectly reasonable, and that limitation is there because we only have an 8-bit port to write. Now it could be written in 2 writes with a couple extra bits to scale it up, but there's really not a lot of point for it in real applications. So what do? You write that count, and then you just pull the timer status location, and the D0 bit is going to be 1 when it's running, and when the count's expired, it'll go to 0. Timer test code is shown here. It's in the GitHub under part B3 test 2. The code will turn an LED on and off. It'll turn it on for 1 second. No, I think it turns it off. Well, I have to read it carefully here, but it turns it off and on. One of them's on for a second, the other is 2 seconds, and when I look at the light, I can see it blinking like it should. So one of the things being shown here is the jump to subroutine. We added that in the previous video, the ability to create a simple nested subroutine, or simple non-nested single level subroutine, and that's passing the counter for that count inside of reg 0. So we're keeping reg 0 use through the program here and reserving it for writing the counter. We also early loaded the register 2 and 3 with LED on and off values, and doing that has the advantage that it doesn't have to access them down here when it goes to do the IO write. It just writes out IO register 2 or IO register 3. So it'll turn, I think it turns it on for 1 second, it goes on for 2 seconds, and then it goes off. So it'll sit in loop doing that back to loop here and loop forever. Never gets back to the start because it loaded those at the very beginning of the program, and the registers stay loaded unless you load them with something different. It did work. It blinked for 1 second on and 2 seconds off. The next thing I want to play with is the J12 connector. That's the IO connector that's on the card. One thing to be careful of with this, I note that VN is on pin 2 and everything here is 3.3 volt levels, so you don't want to use that pin 2 for this. You could drive it from an external source to drive your card if you're hooking it up in a box, and you don't want to use that, I presume. Haven't tried it, but and you don't want to use that barrel connector. You can come in through these, the ground here and the VN over here. But for what we're doing, we're going to be careful just not to use it. J12 physically is located on the card here. You can see the silkscreen J1 or J12 pins 1 and 2, and it goes down through a 40-pin connector. 34 of those pins are available for signals. And note that the pin 1 is close to that DC jack if you're trying to read it. The text on these things is tiny. That little 1 and 2 is very hard to see. That's why I zoomed in here. But I added an entity name for it. It's called IO_J12 because it could be input or outputs, and we'll define that by whatever logic we hook up to it. And I just named it literally the same name as the pins, so the pins go from pin 3 to 36. If you want to refer to it in a sketch, it would just, or in your VHDL code, it would just be IO_J12 and whatever pin number you want. Be nice to create some output data, an output data latch on that J12, and I've got this little card that I sell in my Tindy store for switches and lights. It's got 8 lights and 8 slide switches and 8 push buttons, but it'd be nice to drive those 8 lights out and watch the see how they work. And let's take a look at doing that. I'm going to use the pins that are up here at the top on as marked here, being careful again to avoid the VN pin. Let's add that latch to the memory, and we'll make it read write so the CPU can read it back if it wants, and it's going to go on J12 pins 2 through 9, which is what we show here. Well, actually not 2, it would be 3 through 10, so ignore what I wrote there. It's really 3 on. And there's still plenty of room left in the I/O map. I'd like to do a Cylon Warrior demonstration, and we'll throw a video in here for that or two. It'll be the first presentation with an actual video of the card running. But to do that, I'm missing an instruction, and that's a shift or rotate instruction. It'd be nice to be able to rotate left or right, but I really don't want to take up 4 instructions to do that. Let's find a way to do that and only use one of the 4-bit opcodes. We can encode the shift direction and shift rotate flag in some bits out in the lower bits of the thing. We could implement a barrel shifter by using a count as well, but let's just set the count to 1, but we'll design it so the barrel shifter could be implemented in the shifter. We'll add these 4 new instructions: shift register left, shift register right, rotate register left, and rotate register right. And the difference between a shift and a rotate is whether it pushes in a 0 when it shifts it, or whether it rotates the bit that gets shifted out back in. This is just assuming unsigned math. If it was signed, it would want to shift in a particular sign value. VHDL Entity will have some parts we're not going to use. We don't need the clock, but we'll run it in here in case we want it. We don't really have to have the opcode coming into it, but we'll put it in just to make it only do shifting while it's running. Shift 0 rotate 1 control line, and then a shift left and shift right control line, and a shift count. Now again, that's going to be hard-coded a value of 1, and then data in, and then data out. So data in comes out of the register file. This works just like an AND register immediate instruction. It picks up the register, sends it through the shifter just like it would send it through the ALU, and then shoves it back in. So that's the O data out pins. So that's all the entity would look like. Okay, next step we have to do is hook up the shifter to the CPU, and this is the entity for the shifter that goes inside of the CPU. Again, all the stuff that's on the left is defined in the shifter itself, and the stuff on the right is how it hooks into that CPU 001. First line of clock we're not using. The op SRI shift or rotate instruction is hooked up to a decoder inside of the CPU 001. I've shown examples for that in some of the other videos that are prior to this video. Data 6 gets hooked up to, out of the ROM, gets hooked up into a shift 0 rotate 1. So if it's 0 it'll shift, if it's 1 it'll rotate 1, pulling it out of those bits. The shift left or right control is off ROM data bit 7. We're showing it hard coded here, but in the code I've replaced it with ROM data. The shift count replaced it with ROM data 0 through 2, which sets up this function for the future if we ever build a barrel shifter. At the current moment, it'll just shift 1, and the assembler has to be, of course, altered to fix all this. The data in is the data out of the register file, and the data out of the shifter goes into a set of 8 wires that are the shift out data, which will have to be selected for writing into the register file. Test code is fairly straightforward here, hopefully. We start out by setting up the timer, which we're going to reuse from the timer that we already have, to 255 milliseconds. So give or take a quarter of a second. We'll start out with 1 in R1, which is the bit we're going to shift through the LEDs. They'll write that value out to the J12 port. So that will write that out. The J12 is hooked up to the LEDs. Then we'll wait for that time that's inside the 0 in this wait subroutine. We're reusing the wait routine we wrote for the other example codes. It's a jump subroutine with a return subroutine at the end. Then to check if we're done, we'll first do the shift, and so this will be testing if the shift worked. We'll shift left by 1. Remember, we've hard coded this value, but we have to set it in here, otherwise the assembler will say, hey, I don't implement that yet. But to test if it's done, if we keep shifting a 1 left, eventually it'll fill up with all zeros, because that bit will shift out the left side. So if we AND that register 1 with FF and we get a 0, then we know that we've gone through all the bits. And if it's equal to 0, go back to setting it back to 1 again and go through that order of operation there. And that's really about it. It's stored in the GitHub at part B3 test 3 if you want to try to run it. Hopefully that video was nice to see. It finally good to see something run. Sorry about the quality of the shaky hands. It's just a little bit tough to do it in the current setup I have. I don't have one of those overhead cameras or anything like that, and my overhead lights shine down on the cards so everything's shiny. But anyway, hopefully that gave a little picture of what's wired up here. Let's do what I consider to be the classic demo program for front panel lights, and that's the Cylon Warrior. We'll write some code to do that. It's very similar to the previous code. It'll bounce one way and then bounce the lights the other way. A little bit of a difference here. Instead of ANDing with FF when you're going in the other direction, you AND with 7E. The reason being, one's shifting left, one's shifting right, but you've already been in that 8th position, and you will start out the next round in the least position. So this just shifts it through those bits, and that's really about all you got to do there. Okay, that was fun to watch. I could watch a Cylon Warrior all day. I don't know why. It's just something that's fascinating to me. But we got a card that's got 8 switches and 8 LEDs and 8 push buttons. Why don't we use those slide switches as the timer value, read that and use that as the time to time our millisecond loop. And we can set it anywhere from 0 to 255 and see what it does. We'll add those 8 inputs from the switches that get wired over to this connector. The LEDs came off this connector. We'll wire those over to pins 29 through 36 on the J12 connector. And there's the control lines we're using. We need power and ground both for the switches because they have to be pulled up. And here's the pins they're using, going on the other end of the connector to leave spots in the middle. Let's add that input, 8-bit input ports from the switches. I believe this number is wrong. I think it should be 29 through 36. I believe that's what I set it to. We'll add that to address D, and Before we do that though, let's make sure the wiring is right. Write a little piece of code that reads the J12 switches and writes it out to the LED and just loops forever. And I did that and it worked, so I knew I was wired correctly. Actually, it took a little bit of fiddling around. That was how I learned that this number was wrong. I should have fixed it here in the port map. Sorry about that. But that does work, so you can turn on a switch and the light will go on right above it. Cylon Warrior test code just gets changed a little bit. Rather than only loading that timer for R0, red 0 at the beginning, you load it every time before you call that right. So you load it here and you load it here off that location D, which is where the switch is. And that routine uses that R0 value, register 0 value for the time loop. Okay, well, this was a pretty good video. I think it was for me. I hope it is for you if you stuck with us through this long series. In this video, we added and tested the VGA. We were able to type things on the USB to serial from the computer, have it go into the card, and then have it echo it back and write it up to the VGA screen. It's pretty much half a terminal. Probably the hardest part of the half of a terminal. It's really just lacking a keyboard to hook up to it. We were able to test the UART, which is necessary for that video. We added a timer unit that I had previously designed. It's up in the GitHub if you want to see how it works. That essentially you can write in a loop for, you can do a timer for 0 to 255 microseconds, 0 to 255 milliseconds, or 0 to 255 seconds. You write the timer value. It does sort of a one-shot function. It keeps running until that time is completed, and you can pull that location. There's no interrupts in this processor, so that's how it works. We added 4 new instructions, but we only used one 4-bit opcode, and that supports shifts and rotates, left and right. So that's all 4 instructions. The assembler was fixed to accommodate those as well and generate the right output data and stream for that. Nice function to have the shift and rotate. For the demo we had here, it was definitely useful. We were able to do a lot of stuff without a shift and rotate, but if you're not running the Cylon Warrior, you don't have a computer. A computer with lights. Anyway, part of doing all this is added the connections out to the J12 I/O pin connector. PMOD connectors are really just the same. They're just different pin numbers, and we could demonstrate that, but there's really not a lot of point in it. And we hooked up 8 LEDs and 8 switches and did run that Cylon Warrior demo. Not really sure what to do next. I have to think about it. Nothing comes to my mind immediately. Anyhow, thanks for watching. If this is our last video and you stuck through the whole darn thing, thanks for doing that. I really appreciate it. If not, then you want to get back and look at some of the other ones that are there. And hopefully getting to see the card actually run here in a real external viewable sense with switches and lights and controllable and all that. Hopefully that was fun for everybody that's stuck through this. All right, have a good day. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.